Okay, now we have the Hamiltonian, and that's also write down the Jordan-Wigner transformation, just to refresh your memory. So the sigma I plus is mapped to the creation operator Ci dagger, which creates one fermion at lattice side I, and then we have this ugly face here that you also see in your homework too. Which by the way is due by the end of today. So make sure you finish that on time. So
I got a question on
yep.
that.
Uh-huh.
I was looking at the lecture notes and it said CI plus. Is that supposed to be CI dagger?
Oh yeah.
Okay.
Yeah, you're right. So that could be a little typo because sometimes the dagger and plus looks similar. Yeah. Yeah, right. Yeah, right. Yeah. See, yeah. Yeah, I'll correct that. Thanks for pointing out that, Paul. I remember in the old days when we don't have LaTeX, we can only type the plus instead of the dagger. So the old professors I have in the university always use the plus because they can't type the dagger symbol in PowerPoint or something. Now we have LaTeX, so it's much more convenient. Okay, so this is a Jordan-Wigner transformation, and the phase is actually because we want to make sure that these fermions actually obey the commutation relationship. Like if you create two fermions in the opposite order, you actually get a minus sign. So the sigma plus does not directly map to Ci dagger. You have to have this phase here. And that's a non-trivial part. Okay, so there are a couple of things we can do. So first we can plug in this directly into this Hamiltonian by using the fact that each of the sigma ix is just sigma I plus sigma I minus, right? That's an identity. It's just how the sigma plus and sigma minus are defined. And with that, we can basically rewrite this Hamiltonian. This is the last equation I wrote in the Mondays class. So this looks somewhat complicated, but it's really just plugging in this expression and this expression into that equation here. So we're going to work out this in this class. So this part is for the sigma ix, so this whole bracket I just wrote, and then we also have it for sigma I plus 1x down here. So the only thing that's changing is I is changed to I plus 1 compared to the first square bracket. And then we also have this term, but this term is relatively easy because the sigma z just have this simple mapping here. So far, no magic. We're just plugging in the Jordan-Wigner transformation into the quantum Ising model. Okay, so now we need to simplify stuff. I sort of mentioned at the end of the last lecture that we're trying to just get rid of all these phases, this -1 to something. We're going to get rid of all these. And how do we actually do that? So the first thing I want to mention, which is something I actually probably didn't say correctly, is these two. So these two terms in the Jordan-Wigner transformation, and also these two, they actually commute. So the particular order doesn't actually matter. So to see this, we can basically note that this is basically just a sign. It's either 1 or -1, right? For a particular many-body Fock state. So for example, if you apply this whole operator here on a many-body Fock state, say n1, n2, all the way to nn, right? So this is in the fermion picture. We have ni fermions on the lattice side I, right? So if you apply this whole operator on this, it actually doesn't matter if you swap these two, because this basically, this term there, the space there only gives you either 1 or -1, depending on how many particles you have from I plus 1 to n. And the Ci dagger only creates a particle on the lattice side I. And the sum there does not actually concern the lattice side I, because the sum is from I plus 1 to n. So basically this sign here, whether it's a +1 or -1, it doesn't really matter if you apply the sign first or applying the sign later, right? Because the state is not changed. So in some sense, this is actually, so the state here is an eigenstate of this phase operator. So it is an eigenstate, so it just becomes a number. And because a number always commute with an operator, so it doesn't really matter in this case. You only need to be careful about the commutation when you have something like a Ci dagger, Cj dagger, right? And this actually matters because when you're swapping the two operator, you're actually, swapping the two fermions on different sides. So that would not commute. But in this case, it actually commute. So you can actually, swap these two if you want. So you can actually swap these two. And for the same reason, you can also swap these two. This is just a Hermitian conjugate of the first equation. So they actually commute. So the particular order doesn't really matter in this case. Okay, so with this in mind, we can actually try to simplify this Hamiltonian here. So let's first talk about how we multiply this term with this term, right? So there's going to be 4 terms from from the product of these two square brackets, 2 in each. So that you're going to get 4 terms after you expand this product. So we're going to look at it term by term. Okay, so let's first look at these two, right? So if you multiply these two together, so what do you get? Okay, so let's first write down. So we have Ci dagger, and then we have -1. J is from I plus 1 to n of nj. And then this next term, as I said, these two actually commute. So I can write the phase in the front. So this is I plus 2 to n, and then you have an nj. And then you're going to have the Ci plus 1 dagger, right? The only thing I did is to swap these two operators as they commute. And then let's try to simplify this. So in these two products, you can actually combine the exponential because these operators commute. They're all the number operators. And in this case, you can see that this is actually counted twice, right? Sorry, this part is actually counted twice because j from I plus 1 to n. And the first one also contains that, except for the first term, which is the ni plus 1. And those actually goes to 1, right? So because you're basically having -1 to the ni plus 1 plus 2 times the sum from j equals to I plus 2 to n of nj, right? The 2 is because you can combine the two parts of the sum. And then because the factor of 2 here is -1 to something, and this is always an integer, right? If you apply on any eigenstate, it's an integer. If it's a superposition, it will get you to different integers, but because it's an even number with a factor of 2, the -1 to that power is always 1. So this part is basically gone, right? If it's always 1, then it doesn't really matter. So this actually just reduces to -1 to the ni plus 1. Because this phase operator is either 1 or -1. If it's squared, then it always goes to 1. Okay, so this is the first simplification we can make. But there's still something here, right? And we don't like this one either. So let's see if we can get rid of this one. In fact, this is actually true. So you can actually completely forget about this and just write it as this. So they're exactly equal. So why is that the case? Actually, sorry, there should be always a minus sign here. And the reason is basically the following. So we have a Ci plus 1 dagger here, and we always need to apply this operator on some basis state. And we know that the Ci plus 1 dagger is going to kill the state if you have a state with ni plus 1 equals to 1, right? Because you can't create another fermion. So in this case, the whole operator is just a 0. And it doesn't really matter, how you write it, because if you write it in this way, it's always 0. So even if you have a minus sign, it doesn't really matter, because this one is just going to be different from that one by either a plus or minus sign. So in this case, it doesn't really matter. And then in the case where you actually get 0 particle in the I plus 1 side to start with, then the Ci plus 1 dagger is going to create 1 particle. So you're going to add. So you're going to end up with a state where the ni plus 1 is actually equal to 1. Right, so this is a state you get after applying this creation operator. And then if you look at this phase, now you know that this actually has to be 1. The ni plus 1 has to be 1, so it always gives you a negative sign. So this application of this phase operator always gives you a negative sign. And then you basically have Ci dagger to the left. So this is actually an equality in all cases. So this phase operator, even though it's an operator, it actually just reduces to a -1 sign. So again, the logic is that you can only have 2 cases. You can either have 0 particle on the I plus 1 side or 1 particle in the I plus 1 side. If it's a 0 particle, then this whole operator becomes 0, and adding a negative sign there doesn't really matter. And if there's one particle on side I plus 1, you're always going to get a negative sign because of this phase operator. So in both cases, you can just write a negative sign and make these two operators equivalent. Okay, so that's the simplification we're going to make. And we can make similar ones for all the other terms. So there's going to be 4 other terms here. I'm not going to write every term here, so I'm just going to quickly write the result here. So we also have, let me use a different color here for clarification. So we also have this term multiplied by this term, sorry. And if you multiply these terms together, so this will actually give you, let's see, so the result is just going to be Ci dagger, Ci plus 1. So in this case, you don't have the minus sign. And then you also have this term multiplied by this term. So this is going to give you a result that is Ci plus 1 dagger. In this case, you're going to get a negative sign. And finally, you have the multiplication of these two terms. And this is going to give you a term that looks like Ci and Ci plus 1. So in this case, you also don't have a negative sign. So so the same trick is applied to all 4 terms. And 2 terms get a negative sign always, and 2 terms get a positive sign always. So that's basically how you do it. So with these calculations, we can actually write down the simplified Hamiltonian for this. So that's basically what we said at the end of the class. The Hamiltonian goes to this. So we have an I from 1 to n. I also absorb the minus sign in the front here. So this just becomes Ci dagger, Ci plus 1 dagger, plus Ci plus 1 dagger, minus Ci dagger, Ci plus 1, minus Ci plus 1. And then we still have this term here. And I'm going to ignore the minus 1 here because it really just adds a constant to the Hamiltonian. So it adds a constant of n times g to the Hamiltonian, which doesn't really change any of its property, because a constant is just a constant shift of all your eigenstates, of all your eigenenergies, and only contribute to a global phase for any evolution. So we're going to ignore the constant there. So this is a simplified Hamiltonian. So make sure that you don't forget the minus sign, because here we get a minus of this, and then this minus sign will cancel with this minus sign. That's why I get a plus here. Okay. Yeah.
The limit on that first sum changed from when we wrote it up there to down there.
Which one?
The upper limit is n minus 1.
Oh, sorry.
Is
Yeah, so this
all
should be
numbers in
n.
here, or-
Yeah, so this should be n.
No, that should be n.
The typo. We have periodic boundary condition, so it's always sum to n. Yeah. If it's n minus 1, then it's open boundary condition. Yeah. Okay, so this Hamiltonian, you can also write it even in a slightly simpler way. So you can just write it as Ci dagger, Ci plus 1 dagger, plus Ci plus 1. And then the rest 2 terms are actually the Hermitian conjugate of these 2. So these 2 terms are the Hermitian conjugate of the first 2 terms. And the reason is because if you take the Hermitian conjugate of this, it actually becomes Ci plus 1 in the front, and then Ci. And that is actually the opposite of this, right? Because the fermions anti-commute, so this negative sign actually, is correct. And similarly, if you take the Hermitian conjugate of this, it actually becomes negative of this, right? So it's actually Ci plus 1 and Ci dagger. And if you swap the order, you get a negative. The latter 2 terms are just Hermitian conjugate of the first 2. And this makes intuitive sense because the Hamiltonian has to be Hermitian. So if you have some term and then you add the Hermitian conjugate, you make sure that the whole Hamiltonian is Hermitian. Okay, so this is a nice form of the Hamiltonian, and you can see that it goes back to this quadratic form we kind of deal with when we are talking about, the Bogart-Bove transformation and weakly interacting bosons. Of course, our next step is try to diagonalize this Hamiltonian. So the goal is to actually, change this Hamiltonian again to something that is like a non-interacting, particle. So at the end of the day, we're going to change this to some epsilon k, and then I can call it, something different. Let me just call it fk dagger, fk. So we want to change this to some non-interacting fermions with some diagonalization. Yeah, question.
Just a quick question on notation. Some sometimes I see two Hermitian conjugates. Is this one denote the Hermitian conjugate of both terms?
Yeah, so whenever you have a Hermitian conjugate, it's always a Hermitian conjugate for all the terms to the left of it. Right, so this is actually a Hermitian conjugate of both. Right.
So what would a second Hermitian conjugate in that case?
Which one? So the Hermitian. So this thing stands for the Hermitian conjugate of this plus a Hermitian conjugate of this. Right. And they will respectively give you this term and this. Yeah. Question. Yeah.
I might have missed it, but where did the minus one go in the G term?
The minus one. Oh yeah, you're right. So because it's a constant, so I just ignore it in the Hamiltonian. This is a constant. It's not even an operator, right? So when you sum over this minus one, you just get n, and the minus cancels with that, so it's just n times g. It's a constant in the Hamiltonian, which doesn't make any physical importance, right? Because if you have a constant in the Hamiltonian, if you do e to the I minus IH, it just gives you a global phase. And then if you look at your eigenstates, it's not going to change at all, right? A constant cannot change the eigenstate. And the eigenergies get shift, can all get the same shift, which doesn't really matter because you can always choose a reference energy point. Right? It's only the difference between the energy levels that matters. So usually we ignore any constant from the Hamiltonian, just for simplicity. Okay. So before we proceed to this diagonalization, I want to actually ask you one question. It's actually an important question, which is the reason why I went through this ugly math of trying to show that you get to this Hamiltonian from the Jordan-Wigner transformation. So I want you to think about the following question. So let me use a different color here. So now assume we have next nearest neighbor interactions. So this means in the Hamiltonian, we actually have terms like, so let's just create a different Hamiltonian here. So the IC interaction is between the side x and side I and I plus 2. So it's next nearest neighbor. It's just the neighbor ones, but it's the next nearest neighbor. Suppose I actually have a Hamiltonian like this, right? I can forget about the transverse field term. So, let's see if we can do Jordan-Wigner transformation on this. And we can use the same trick we have here before, right? We can actually change all these sigma x to the Ci and the Ci dagger. So, so this first part here will not even change. So actually, let me write this, transformation explicitly to help you. So, and then I'm going to ask you a question there. So we have Ci dagger minus 1 to the sum j is from I plus 1 to n of nj, and then minus 1 to the sum j is from I plus 1 to n of nj and Ci. So these correspond to the sigma I plus and sigma I minus. So this is exactly the same as what we write here, right, for this. And now for the second part, because it's I plus 2, so I'm going to actually, just change I to I plus 2 for the first term. So this will be I plus 3 now of nj, plus this second term is actually just a Hermitian conjugate. Ci plus 2. Right. And my question is, if you follow what we did, above, can we actually sort of simplify this to something very similar to this? Can we actually simplify this to a Hamiltonian that is like Ci dagger, Ci plus 2 dagger, plus Ci plus 2 dagger, plus the Hermitian conjugate, right? So whether we can actually get something which looks very similar, you just change I plus 1 to I plus 2. Is it actually possible? Or is this one actually only true if you have nearest neighbor Ising coupling? So I want you to think about this. If you think this is actually correct, you can pick choice A. And then if it's incorrect, you can pick choice B. And if you don't know the answer, you can just say, I don't know. So I want you to think about this. This is actually kind of an important question. Again, A is for correct, B is for no, C is you don't know. And I want to scroll up here just to give you some hint of what's going on here. So the difference is that here we're going to have, instead of I plus 1, we're going to have I plus 2. And this sum is going to be I plus 3. So is it still possible to do this reduction? right, to just, for example, a minus of this, if I plus 1 is changed to I plus 2.
And so we've replaced.
Yeah, we would just replace the I plus 1 there to I plus 2, right? So it's like the next nearest neighbor. And can we still have this nice, structure that you can remove the face operator there? Kind of trying to help you understand it. I write the equation there, the question equation. It's right there in purple. Okay, if you have an answer, make sure you use a clicker to answer it so I can get some statistics to see whether you're understanding this. Yeah, if you don't know, just say don't know. Okay, we don't have too many people here, but I think most of you get it correct, so the answer is no. So this is actually not possible. And the reason for this is actually not that complicated. Again, let me use a different marker here. It's orange here. Okay, so you see that if we follow the same derivation I did here, then what's going on is these two ones will cancel to the minus 1 to the ni plus 1 and plus ni plus 2, right? Because now this is starting from I plus 3. Starting from I plus 3, they will be canceled because you are having two of the same faces, which always square to 1. But then you will have ni plus 1 and ni plus 2. And we can use the same trick to remove the ni plus 2 because the creation operator is on the right. So then you're always going to deal with either no state, that the state is killed, or the state where there's one particle in I plus 2. So this one is always 1. So ni plus 2 is always 1. But the problem is you have another term, which is ni plus 1. And we actually don't know whether ni plus 1 is 0 or 1. Because it depends on the state you're acting, right? If you're acting on the state of ni plus 1 equals to 0, then this will be a phase of 1. Otherwise, it will be a phase of minus 1. And if you're in a superposition state, then you are screwed, right? So that's a problem. So then this means this operator cannot be reduced to, right, a simple sign, right? It has to be an operator there. So the best you can do is to actually add an operator of minus 1 to the ni plus 1 here. Right, so that's the best you can do. And this operator, this is a phase operator, so it does commute with both of the two. So you can put it either in the front or in the back or in the middle. But that doesn't matter because it's just a sign. It wouldn't change how you create the fermions, right? It doesn't change the order. You just add a sign to your state. So this one apparently cannot be reduced to that, right? So you can't ignore this phase operator. So that means if you have just next nearest neighbor interaction, you can't actually get a nice quadratic Hamiltonian. The best you can do is to include a phase of this, at these different places. And unfortunately, once you include the phase, this is no longer a quadratic Hamiltonian. You can't use any trick we learned, like this Bogart-Ball transformation, this diagonalization of non-interacting fermions, to make it into this nice, form. So this whole diagonalization would not work if you just include the next nearest neighbor interaction. And for the same reason, if you have just nearest neighbor interaction in 2D, this is also not going to work. The Jordan-Wigner transmission itself works for any dimension. You just need to label all your lattice sites. If you have n spins, you just need to label them, from 1 to n. But the problem is kind of similar to the case with next nearest neighbor. So suppose I have a two-dimensional lattice with n spins, I can always label the lattice as 1, 2, 3, 4, right? And then 5, 6, 7, 8, say 9, 10, 11, 12. And then the problem is you are going to have interactions with the neighbors, which is like sigma x1, sigma x2, which is fine. But then you're also going to have interactions in the other dimension. You're going to have a term of sigma 1x, sigma 5x. And that is bad again, because this is kind of like also long range. And you're going to get operators like C1 dagger and C5 dagger, but with the ugly face that now will include N2, N3, and N4, right? Because see, this phase is always like, for the particle, you have to count the particles in between of these two sides. And that is bad. So this is phase operator. We have no idea how to analytically solve it, right? You can, for the same reason, the Jordan-Wigner transformation would not work for two-dimension, even with nearest neighbor interactions. There are some more advanced tricks that can simplify this in 2D a little bit, but in general, you don't get exact solutions. And you only get these non-interacting fermion solution, which we're going to talk about when you are in 1D with nearest neighbor interaction. So this is the reason why I say that this is one of the very few many-body Hamiltonians that you can actually solve it analytically. It's very restricted. You have to have one dimension and with nearest neighbor interaction. Only in this case, you can map it to non-interacting fermions. So now the question is, what if you actually have long-range interactions in the Hamiltonian? And in particular, for example, the trapped ion quantum simulator, they actually are famous for having long-range interactions. It's one of the advantages that you can actually do faster quantum gates and build a faster quantum circuit. So in this case, of course, the Jordan-Wigner transformation will fail. Unfortunately, there's another transformation we're going to learn later. It's called the Hoston-Primakov transformation. You're going to map the spins to bosons. So in that case, you don't need to worry about this. Whether they're nearest neighbor or next nearest neighbor or long range, you can always do the mapping, and it's always quadratic. But there's also a price you have to pay. You have to make some assumptions. The state has to be very close to the state where all the spins are polarizing in one direction. So you can only work in some very particular state, close to some very particular state. While here, this if it works, then it works for any case. It's exact mapping from the spin model to the fermions. So there's always some price you have to pay. Yeah. All right, any questions? You can also think that this is kind of the reason why we need a quantum simulator or quantum computer, just because these spin models or interacting qubit models are so hard to solve. There's only very limited cases you can have exact solutions independent of the number of particles. Okay, so now we can try to diagonalize this Hamiltonian. So let's sort of first rewrite this this fermionic Hamiltonian we have. So it's basically this one. Let me highlight it here. So this is a Hamiltonian we're trying to solve. And I wish that this is a simple process, but in fact there's something else that I need to introduce before moving forward. So let me first rewrite the Hamiltonian here. Oops. So H is I from 1 to n, Ci plus 1 plus Ci plus 1 dagger plus Hermitian conjugate, then minus 2g. So there's actually one issue with this effective Hamiltonian. So far everything works, but you have to consider this periodic boundary condition, which I actually haven't emphasized. So if you have a periodic boundary condition, so this is actually the reason why I, in the lecture note, I actually write n minus 1 here. It's actually not a typo. So this technically is only true for n minus 1. So the last term has to be treated separately. And the reason is simply because this boundary term looks like a C1 dagger and a C, n dagger, right? Because when you set I equals to n, so this is, we can write it in the opposite way. So it's actually C n dagger C1, right? Because n plus 1, C n plus 1 dagger is equal to C1 dagger. by the periodic boundary condition. So the boundary term actually looks like this, and there are similar terms here. So this would be, Cn C1 dagger, and its Hermitian conjugate. And these terms actually you can't quite cancel the phase. So there's a problem here because as we said that this, when you do the Jordan-Wigner transformation, you have to insert the phase operator, which counts how many particles you have between the two, in this case, between the site 1 and n. So there should be a phase factor that looks like n2 plus n3 all the way to, n minus 1. So there actually should be a phase factor like this, right? So that means technically that expression is wrong. So if you include the I equals to n term, you need to deal with this. So that's sort of the extra complication we have to deal with. And there's some tricks you can play with this. So first you notice that because this is always like a C1 dagger on the left, you can actually change this to, this summation can actually be reduced to just -1 to the sum of the total number of particles. And the reason for that is you're always creating two particles at site 1 and n. So whenever you apply this phase operator, you either apply it to a state to a null state because you can't create more fermions if there's already one on either site 1 and n, or you're always going to deal with a state where you have exactly one fermion at site 1 and n. And in this case, these two are actually equivalent because I'm just summing over n1 and nn, which are both equal to 1. So that's you are doing -1 to the 2, which is always 1. So these two are actually exactly equivalent. And similarly for all these other terms. So this actually means this boundary term, sigma 1x, sigma nx, which is basically the term I'm writing here, that actually can be simplified to, with a minus sign in the front, we have -1 to the sum of j from 1 to n of nj. So this is a total number of, this exponent is a total number of fermions with the Cn dagger, C1 dagger, plus Cn, C1 dagger, plus the Hermitian conjugate. So that's a boundary term we have to deal with. So the previous Hamiltonian is only true if you limit the summation to n minus 1. Although this is much simpler, the problem is you can't do the discrete Fourier transformation because that requires the system to be periodic. So we have to deal with this boundary term, unfortunately. But this is still analytically solvable because, if you look at this, this is a total number of fermions. And this phase here, this is a phase operator you can't actually kill, right? It actually has to be there. But because it's only regarding the parity of the total number of fermions, whether it's odd or even, you can basically just try to solve the Hamiltonian in two separate cases. One is that the total number of fermions is odd, and the other is that the total number of fermions is even. So you just need to do two cases separately. So the complication, we add to the periodic boundary condition is just that you have to solve this diagonalization problem for two different cases. One is total number of fermions being odd, and the other one being even. And this seems to be kind of like a mathematical consequence, but this kind of exactly gives you this near degeneracy we talked about in the last lecture. These two ground states, right? They're almost degenerate when the transverse field is small. You have this exponentially small gap. So it's kind of important. You have to actually have that. So we basically have two cases. The first case is the total number of fermions is odd. So basically the sum over j and j is an odd number. So in this case, this whole thing here, this boundary term, just reduces to C1 dagger, Cn dagger, plus C1, Cn dagger, plus the Hermitian conjugate. Yeah, sorry, I think I have a minus sign here. And then there's another case where the total number of fermions is even. So in this case, you will basically have the opposite of this. So sigma 1x, sigma nx is just going to be the plus sign of this. It's basically this is going to change its sign. I get a minus sign because I'm swapping the order here. So that makes a sign difference. so for these two, we can also sort of make these two situations a little bit simpler. So this one actually corresponds to a boundary condition where we can simply just set Cn plus 1 to C1. And this one we can actually just summarize it as basically setting Cn plus 1 to minus C1. So if you do that, this Hamiltonian here is actually technically correct. So the only thing we need to do is we have to redefine the boundary condition. So the Cn plus 1 is going to be either equal to C1 or equal to minus C1, depending on the odd or even. So this is odd number of fermions. So this is even total number of fermions. So that's sort of the take-home message here. So you can still use this quadratic Hamiltonian. The only difference is that this boundary creation operator is going to be defined in different ways. So it's either periodic or anti-periodic. So this is also called the anti-periodic boundary condition. So that's the complication we make. But in either cases, we can actually try to solve this, try to diagonalize this Hamiltonian. Okay, so with this sort of extra nuance, we can now proceed to diagonalize this fermionic Hamiltonian. So this diagonalization is going to be similar to what we have in the weakly interacting bosons. So the first thing is we're going to introduce the discrete Fourier transformation. So in this case, I'm going to use the operator A here instead of the F. So I'm just going to change these two to A to avoid any confusion. So I'm going to diagonalize. Actually, maybe I should still use F because there's a Bogly-Wolf. At the end of the day, we can, yeah. So actually, I use the notation B here. So let me first introduce the A operator, which are the creation and annihilation operator of the actual fermions in the momentum space. So same discrete transformation, discrete Fourier transformation as before. And then this is the inverse discrete Fourier transformation. By the way, if you get stuck on homework problem 3 of your homework 2, this inverse Fourier transformation should help you. So this is like for the non-interacting fermion case, without a parenton, I ask you to diagonalize the Hamiltonian. So that's a problem in homework 2. And this inverse transformation should help you. Okay, and by these two Fourier transformation, we can actually first try to change this Hamiltonian here. So this Hamiltonian here to the momentum space. So basically, we use the AK operator, which are the annihilation operators for the fermions in the momentum space. So this is going to give us something kind of very close to what we have in the non-interacting fermion case. So we're going to get this cosine 2 pi k over n. And then minus g. G is the transverse field, so that's always there. And then we have AK dagger AK. And that's not the end of the story because we have these pair creation and annihilation operators in the journal in this effective Hamiltonian. Let me just highlight this Hamiltonian here again. So this is the fermionic Hamiltonian we're trying to diagonalize. So we are going to have these pair terms still surviving. So it's going to have a sign. And then we have this AK dagger, A minus K dagger, plus the Hermitian conjugate, which will basically have two AKs. So that is the same fermionic Hamiltonian, but now, changed to the momentum space. So we also talk about there's a boundary condition difference for these two. So how would this boundary condition reflect in the Fourier transformation? Actually, the result is kind of simple. So basically, if you have Cn plus 1 equals to Cn, if you have the usual periodic boundary condition, then what we have is that the k is an integer. So k is basically going from 1 to all the way to n, as usual, because you just have the periodic boundary condition. But if you have the anti-periodic boundary condition, the only thing you need to change is k is going to be a half integer. So k is basically equal to 1/2, 3/2, all the way to n plus 1, n plus 1/2. So this is a small nuance we have to deal with because of the periodic boundary condition. Okay, but in any case, the Hamiltonian takes the same form. The only difference between these two cases, which depends on the total number of fermions being even or odd, is basically the choice of k, whether k is integer or half integer. So once you get to this Hamiltonian, the next thing we need to do is to get rid of these pair creation and annihilation terms. And that's kind of the old game we learned before. It's the Bogdanov transformation. But in this case, it's going to be a little bit different because the ones we learned in weakly interacting bosons is the Bogdanov transformation for bosons. And here we have to do a Bogdanov transformation for fermions. And they are kind of very similar. There's only a subtle difference here. So if you remember the Bogdanov transformation, we introduced these BK, this quasi-particles creation and annihilation operator. And instead of getting the cosh function, you're now just getting a cosine function. And it's kind of related to the difference between the commutator and anti-commutator for bosons versus fermions. And you're going to be asked to prove this in your homework 3. So don't worry about if you can't understand these equations. So this is the Bogdanov transformation for fermions. There's also a Hermitian conjugate version, which you just take the Hermitian conjugate of the top equation. But the minus I will become plus I here. So that's the Bogoliubov transformation for fermions. All right, so with this transformation, you can actually get rid of the pairing term. Of course, you have to choose your theta k, which is a Bogdanov angle correctly. In this case, the choice is kind of also similar to the boson case. We need to have the tangent instead of the tang. The tangent to theta k has to be equal to this particular function. So if you set these angles correctly, and then you're going to end up with a beautiful Hamiltonian, which is simply epsilon k, bk dagger, bk, minus 1/2. So that's what you're going to get. The minus 1/2, again, is not very important because it's just a constant energy shift. It's not an operator, it's just a number. And the important part is the energy spectrum. Again, I'm not going to bore you with the actual derivation of how we get to this. It's purely algebraic, and you can trust me on these calculations. These are actually correct, these results. Again, we have these cases. The k can be either odd or even, so k is going to be, k is either integer or half integer. So it depends on the total number. So if the total number of fermions, let's call it n fermions, is odd, in this case, and total number of fermion is even. So there are two cases. And that's the energy spectrum here. So, so at the end of the day, we actually, basically map the Hamiltonian to non-interacting fermions, and the ground state is just given by, the energy spectrum is just given by the energy, the total energy of a bunch of non-interacting quasi-particles, which are still fermions. Okay, so now with this analytical solution, we can basically find the ground state energy and also even the excited state energy. We can even find the ground state analytically. So what are we going to learn? So now, we're going to talk about the physics once we have the solution. So here we can talk about what the quantum phase transition actually means with this analytical solution of the eigenenergies. Okay, so for simplicity, that's going to assume that the G is larger than 0. So basically the field is positive, but the negative case is basically similar. It's very similar. You can basically also just flip all the spins. So we're just going to focus on the G larger than 0 case for simplicity. You can see that this is pretty much symmetric. Even if G is negative, the cosine there, you can flip the sign there. So it's going to be symmetric. Okay, so let's first look at the expression of epsilon k. So the first thing we notice that this is actually minimized when the k is equal to n, right? Because in order to minimize this epsilon k, so we're trying to find the bottom of the of this band structure, right? Because this actually this epsilon k, you can plot it as a function of k. K still stands for momentum. It's the lattice momentum we talked before. You're going to find where it touches, where it's actually minimized. So this actually also looks, something like a parabola. But let's first find the minimum. So this is minimized when the k is equal to n, because when the k is equal to n, when the k is equal to n, this cosine is actually going to be 1, right? Because you are just going to get cosine of 2 pi. So cosine 2 pi is 1, and then you get a negative sign. So this is why I have to assume g is larger than 0. If g is smaller than 0, you have to look at the other case. So k is, this is going to be minimized at k equals to n over 2 instead of n. But it's very similar. So in this case, the minimum value of epsilon k, which is also equal to epsilon n, is just going to be 2 square root of 1 plus g squared minus 2g, right? And we know that this can be just simplified. This is this whole thing here is basically just g minus 1. I have to take the absolute of that because I'm taking the square root, right? So the g could be smaller than 1. So that's the expression. So this is kind of where the bottom actually lies in. So this whole, I believe this energy, this dispersion relation, so here is minimized at n. And if you look at, let's see if I have a plot here. I don't have a plot here, but it's actually going to look, I think it's probably going to look like something like this. So that's what the epsilon k looks like. And it's going to be periodic in n, so it's going to look like this. So if you look at the band structure, that's what it looks like. But here, let's just look at what this actually means. So if you look at the minimum a single particle energy, you actually already get a non-analytic point here. So this is actually already telling you that there's something weird happening when the g is equal to 1, because this absolute value is non-analytic, right? So if you just look at the lowest single particle energy here as a function of g, you're actually going to get something like this, right? You're going to get basically a kink here, because it's an absolute value. So this is discontinuous as g goes from a little bit smaller than 1 to a little bit larger than 1. Right? So this is already a strong indication that something is non-analytic at g equals to 1. Okay, so this is, we still need to figure out what's the ground state energy, right? So how do we figure out the ground state energy? Again, because these are fermions, and this is the lowest energy, and then the idea is similar to what we said before, right? So in order to find the ground state energy, you are going to fill in all the energies which are negative, and then leave 0 fermions when the energy is positive. And since here the energy is at is going to be at least 0. So you're basically going to get a vacuum state in the ground state, except that when the g is equal to 1. If g is equal to 1, then you actually get a 0 energy, a mode, which you can either have 1 fermion there or 0 fermion there. So in this case, this is kind of related to the degeneracy we talk about. But other than that, you are just going to get a vacuum state. So for any g not equal to 1, ground state is vacuum of all Bogoliubov fermions. So basically all these BK dagger BK, the number of Bogoliubov fermions is just going to be 0. So it's again a vacuum state. And as we said before, the vacuum of the Bogoliubov fermion does not actually mean the vacuum for the real fermion, because the Bogoliubov fermion is actually a combination of the creation and annihilation operator. So it's kind of a combination of a real fermion and a real hole. And in this case, the real fermion does have a meaning. So the real Jordan-Wigner fermion basically tells you that whether the spin is flipped, right? So if the spin is pointing down, then there's no fermion. If the spin is pointing up, then it's actually a fermion. right? So, but because the Boglie-Ball fermion is a combination of this, so even if it's a vacuum for Boglie-Ball fermion, it's not necessarily a vacuum for the real fermion, which actually means the spins are not necessarily all pointing down. Right? Some spins can be pointing up, some spins can be pointing down. That will correspond to a finite number of excitations in the fermionic picture, just because you have both the particles and the holes. So the actual ground state is going to be much more complicated, but you can actually calculate it with the knowledge that you know the ground state is the vacuum of these Boglie-Ball fermions. And the other thing we have to think about is, especially for g equals to 0, we have to also think about the parity, which is the total number of fermions, because as we said, it seems like when the g is equal to 1, you can actually have two exactly degenerate ground state, right? You can either have basically 0 particle or 1 particle in this mode. But there's actually a problem here because these expressions only work if you fix the parity, depending on the value of the k. For example, here we said this is minimized when the k is equal to n, right? So that would be that basically corresponds to the case where k is an integer. So this actually requires the total number of fermions is odd. So in this case, you have to always fill 1 particle in this epsilon n mode. So you can't actually have a degeneracy because the 0 actually belongs to the other sector. So in some sense, this Hamiltonian is block diagonal. Depending on the total number of fermions, you have it's either odd or even, and you get different energy eigenstates there. So you simply just cannot have a twofold degeneracy even at g equals to 1 due to this parity concern here. And you can actually calculate the ground state in both sectors separately. So there's going to be a ground state in the periodic boundary condition sector. So basically in this sector here, and that's going to be given by the sum over this expression. And here I'm actually explicitly keeping the 1/2 here because it does make the actual energy is actually so the energy the total value of the energy is actually important because these different sectors. And then for the anti-periodic boundary condition here, we're going to have a slightly different expression where the k is actually summing to 1/2. Then n is this is going from 1/2 to n plus 1/2, and then we have the same expression here. So the ground state for these two sectors are actually going to be a little bit different. You never have the exact degeneracy even at g equals to 1 because of this parity of the total number of fermions. So these two expressions look very similar. The only difference is that the sum, one is from 1 to n, the other one is from 1/2, 3/2 all the way to n plus 1/2. Okay, so now I want to ask you another question here. So what do you think will be the difference of these two energy? So when you're doing this sum, and I'm just shifting the sum from integer to half integer. So what do you think will be the energy of the difference of these two energies, especially as n increases? Will that be a finite difference? Would that be a difference that's vanishing in n in some polynomial way, or is vanishing in n in some exponential way? I'm going to give you 3 choices. So the first is the energy difference between these is going to be some finite value. And the second is that this energy difference is going to, decay as some power law in n. And the third is this is going to decay in some exponential function in n. Can you make a guess of this? Okay, this question might be a little bit hard, so let me first give you some hint here. So we know that when we are doing summations, if the n is sufficiently large, if you're actually summing over many, many terms, then both of this is going to become an integral, right? So in the large n limit, So both of them can be converted to the same integral, because in this case, it doesn't really matter. So think about that. You have some function here, so which you are basically trying to sample. So as I said, this is going to be some, this is just the epsilon k, so it's going to be some smooth function in k. So I'm just going to draw some function here. And then the sum here is essentially getting the area behind this curve, right? Because we're doing a Riemann sum here. And the larger n is, you're trying to sample this, trying to get this area more accurately, right? So as you have the infinite number of n here, you're basically trying to exactly do an integral for this area. So then we know that at least when the n is sufficiently large, these two results should exactly match, right? Because they both become the integral of this function here over the area from 1 to n. And the interesting thing is, if n is finite, well, that difference actually shrinks in a polynomial way or an exponential way. So that's kind of the interesting part. And this is actually not so obvious. When I first looked at this, I was kind of surprised that this difference actually can be exponentially small. Because I thought, right, even though I know it's going to vanish in the larger limit, it seems like, I'm making a finite difference. So one is, integer, the other one is half integer. So, but if you really try to do a numerical calculation, even just using Mathematica, you'll be surprised to actually find that the difference goes exponential. So this is the exact energy difference I was plotting here. So it's the ground state of periodic versus the ground state of the antiperiodic. And then this is the number of spins I have. So if you look at this difference, so this is for g not equal to 1. For g equals to 1 is slightly different. So this is for g not equal to 1, so we're not at the critical point. So you can actually see this difference here follows a perfect exponential decay. So see the vertical axis, this is a log plot, this is 10 to the minus 20, this is 10 to the minus 30. So it's like so small, it's actually an exponential decay. So remember previously when we have this intuitive perturbation theory argument saying that if g is small, then the difference between these two degenerate eigenstates should be exponentially small, right? It's not exactly degenerate, but it's nearly degenerate. But now we can actually calculate this difference exactly with this analytical solution. So we actually get an exact calculation of the difference, and we actually show that it's perfectly decaying exponentially. And it's not only for a very small g. So with this analytical solution, we can even calculate for g equals to 0.5, right? It's not a very small g, and it still decays exponentially. So that's the beauty of analytical solution. You can actually get a very nice line here. And not only this, you can also calculate the energy difference when you're at g equals to 1. And here's the interesting thing. If g is actually equal to 1, then this exponential decay here actually now becomes a power law decay. So now you can see that I'm plotting the same thing. The only thing I'm changing is that g is now equal to 1. So the calculation I'm doing is exactly the same as before. So I'm just calculating these two energy. And then look at the difference of the two and plot it as a function of n. So I can do it for g equals to 0.5. I can also do it for g equals to 1. And if you do it for g equals to 1, then suddenly this scaling becomes very different. You can actually get an exact 1 over n scaling. So it's pi over 2n. You can calculate this exactly. So this g equals to 1 is actually the critical point, because you can see that the behavior of the degeneracy, basically the energy difference, we also call it energy gap, between the lowest, the ground state and the first excited state scales in a totally different way. So it goes from exponentially small to only a power law small. So it's only 1 over n. So later on, we're going to talk a little bit more about why this scaling should be 1 over n instead of maybe 1 over n squared or 1 over n cubed. This 1 over n is also something very beautiful. It's related to something called conformal field theory. It's a very hard topic, but I want to sort of mention some fun part of it because this actually relates to some interesting black hole physics. So that 1 over n, just keep in mind that this is something we're going to talk about in the future. It actually corresponds to something deeper for our universe. And then what about g larger than 1? For g larger than 1, it's actually sort of trivial because we know that we don't have these nearly degenerate eigenstates. We already said it in the last class. In the paramagnetic phase, in the paramagnetic state, the energy gap is finite because the ground state is unique, right? Especially when the g is very large. The ground state is all polarized in the field direction, and it takes a finite energy to flip one spin. And that's exactly the case. You can see this top plot, I'm still looking at the energy difference, but for g larger than 1, you can see that the energy difference is no longer 0. Even for very large n, this is actually plotted for n equals to 100. You can clearly see that you get to a finite energy gap between these two lowest lying ground state. And this energy gap is simply given by 2 times G minus 1. And the reason for that is also intuitive because the 2 is really because we are flipping from -1 to +1. And the G minus 1 is kind of the field strength above the critical point. And because of this, you can also clearly see that there's going to be a phase transition just looking at the non-analytic, so this kink here at G equals to 1. So we're looking at the energy gap of the system, right? So what's been plotted is the energy gap, the difference between the ground state and the first excited state. So you go from an exponentially degenerate to lowest lying ground state to a polynomially small gap, and then the gap becomes finite. So that's what's going on for this transverse field IC model. All right, questions, Brandon?
Why do we expect the critical point to follow the power law?
As I said, in general, you don't need to have exactly a power law, right? And the reason why it's a power law is something much deeper, and it's actually because at this critical point, you have something called the Lorentz invariance, and at the critical point in the quantum field theory, what's going on is that the time actually acts in a similar way as the space. And this is also kind of related to what I said. A quantum model can actually, in 1D, can actually be think about as a classical model in 2 dimension. And the other dimension is actually is sort of the time dimension there. And it's really not the time. You can think about it as an imaginary time in the field theory. But you have some sort of strange symmetry there, in both the time axis and the spatial axis. And because of that, this model is actually described by a conformal field theory. It's actually it's called the conformal symmetry. And it is this conformal symmetry that always gives you this 1/n scaling of the energy gap. So, the reason why this is interesting, there are a lot of models in 1D. You're going to find at the critical point, the gap is 1/n. So this is why it's non-trivial. At this point, if you don't understand those, this is just falling from the solutions there. Right? We have these analytical solutions here. And we can just calculate it, and it just scales as 1/n. There's really, it's just like a magic. But there's a deeper reason why that's the case. It's actually not just for this model. It's for many similar models in 1 dimension that you get this 1/n gap. Yeah, George, you have a question too.
Yes. So why is the sum when n is even from 1/2 to n plus 1/2? Isn't there like one more term? Like you sum up for n terms, and when n is odd, you sum up for n minus 1.
I think this is probably a typo. I think this should be not n plus minus 1, it's n plus 1/2. I think I...
But I mean that. In notes,
Yeah.
you had n plus 1/2, so why is it n plus 1/2? Not n minus 1/2.
If it's n minus 1/2, are you summing over one last term? Because, in the... So let me switch to the note here. So in one cases, you are summing from 1 to n, right? And if you try to shift it by 1/2, then the upper limit should be n plus 1/2, right? Just to keep the same amount of
Yes,
terms in the summation.
But then you would start in 3/2.
Why am I starting?
Like, because you start instead of 1 to 1/2 and instead of n to n plus 1/2. So like you're like stretching the sum.
Well, the range is still given by... Oh, you're right. I think you're right. Damn it. I think I actually have the correct ones in the note. So this should be minus 1/2. You're right. You're exactly right. Yeah. So, yeah. Thanks. So you're right. The range is actually n minus 1. If you look at the last one and the first one. So this should be n minus 1/2. Yeah, you got me again. Yeah. So yeah, it's n minus 1/2. Yeah. So the ones I have in typeset note is actually correct. Yeah. Question.
Is there a way that we could have told that the energy gap difference would decay exponentially versus polynomially?
Yeah.
Without graphing it?
Yeah, that's a good question. I actually thought about this myself as well, and there's just no good way I can get an analytical expansion out of the difference of the two. The best I can do is just to graph it. The only thing I can tell you intuitively is that as n becomes infinity, these two should be exactly the same, right? Because they both change to integrals.
Down to B and C with that logic, but to actually know the
Yeah.
true relation.
Yeah, so that's why I didn't ask you the answer. I kind of feel like this is too hard unless you make a totally random guess. But we know that it has to be either B and C. It has to decay to 0. But whether it's exponential or power law, actually I don't have a good intuition to explain this other than just graph it. I actually did this graph myself, so I know this is correct. Yeah, but if you have a better intuition, just let me know. I'll be really impressed. Yeah, it's kind of like a simple math equation here. And in a lot of cases, you're going to see that in these many-body physics, at the end of the day, you get some really interesting math problem. I think later on we're going to make one of my favorite math questions. If you have a series that is just 1 minus 1 plus 1 minus 1, what is the value of that sum of that series? So I'll ask you that question at some later point. It's actually a really fun question. Yeah. Anyway, it's always regarding this infinity. When you sum over something infinite, something fun is going to happen. And that's many-body physics. We're talking about large N here. All right, so I'm going to end the class here. And I'm going to assign another homework 3 by the end of today. You again have 2 weeks to do it. All right, have a good week, rest of your week.
Doesn't that put it due during spring break, of course?
The next one is probably going to be, the spring break will count, right? So it's going to be 3 weeks. Yeah, you're right. Yeah, homework 3 will be due in 3 weeks.
Which I think isn't actually supposed to converge in the first place. I think the particular one I think is minus isn't actually. Right, yes. Yeah, it doesn't converge. Yeah. If you do it wrong, it converges to minus 1. Exactly. But if you do it right, give me a second.
Aaron, what did I say? It converges to what?
So
Yeah.
it's not that serious, but there was something going around the internet a few years ago about somehow the sum of every integer converging to minus 112.
I think it's every
Yeah.
integer from 1 to infinity.
Somehow it becomes minus 112.
Yeah, you can search on YouTube. There are,
Yeah.
I think one guy made a lot of fun videos of how you sum over these series. You get
it wrong, you get minus
a lot of weird answers, right? It's like crazy.
I don't know how you do it wrong to get minus 112. You get minus 112 if you do it wrong.
I was kind of
But
curious with
obviously, it
the
doesn't actually.
-1 thing producing an operator.
Oh, you mean this -1 to some nj, right? Sum over that.
But if it's
Yeah, you want to do the Fourier transform.
Or whatever. Yeah.
Did you have like K and Q like the sequence?
Yes. Yeah. Whenever you have a multiplied sum, you want to differentiate.
Yeah, okay, yeah.
why is that not becoming -1 to the?
Even though.
No, this is actually an operator, right? So this is an operator.
That's an operator.
This is the operator. Yeah, this is not a number, right? Yeah. So okay. Yeah, I think there's a simple confusion here. This nj plus 1, the plus 1 is in a subscript, right? So we're talking about nj plus 1, not nj plus 1. Right, so that's why you can't add these 2 to 3, and then this sum.
That
to
would
2j.
that makes sense.
Yeah.
I was
it's
kind
a-
of just sitting there.
yeah.
I was thinking I was
Yeah,
missing
yeah,
something,
it's
but
kind of hard to write these down, and they're all small in this superscript. Yeah. Yeah.